We've done a rod of charge in class in terms of getting the potential, but what if we want electric field? So let's say I've got a charged rod of distance A through B for the length of the rod, and I want to find the electric field at a position right here, let's say, and I don't want electric potential now, I want electric field at that position. So our driving integral for voltage was equal to the integral of dq over 4 pi epsilon naught r. Well, the driving integral for electric field would be the derivative of voltage. So what would that equal? Well, the derivative of this equation is then going to be, we're going to take the integral of negative dq over 4 pi epsilon naught r squared. So if I take the derivative of this, that equals this right here. So this becomes our driving integral for electric field. So there's our first difference when we're calculating electric field versus voltage. The second difference comes from the fact that electric field is a vector. So we need to consider direction in this. Now, of course, electric field, there are electric field lines going this way and up and down from here. They're also coming out of the board and into the board. Okay, but those are all perpendicular to our spot, and those lines aren't going to affect what's happening at this spot. It's only the lines that are in the x direction that would actually affect this location here. So we're only going to be dealing with, for this example, the electric field in the x direction. So we have to define what is unique, the unique direction that affects the electric field at the position that we're interested in. So we're only going to be doing x direction. We don't need y electric field, and we don't need z electric field. So very similar then to what we did with electric potential, we need to start with our dq value here. We're going to assess a lambda, of course. Lambda is charge per unit length, and I'm going to use the letter x to represent the length of this bar. Now, of course, we need the differential of charge, dq, would then equal lambda dx. And we're going to substitute x, okay, for our r in this case. So then our e in the x direction here, and I'll just keep labeling that x since we are vectors here, is going to equal then the integral of negative lambda dx divided by 4 pi epsilon naught x squared. And our limits of integration are going to be a to b. Now, like always, it's a good idea to pull all the constants out to make the integral easier to do. So that's going to equal then, I'll have a lambda outside divided by a 4 pi epsilon naught. And the integral from a to b of dx over x squared. And let me pull my negative out of that also. Now this, of course, the integral of this is going to be negative 1 over x. So then I will have a negative lambda over 4 pi epsilon naught multiplied by the definite integral of negative 1 over x from a to b. Now what I'm going to do to make things simpler is I recognize I've got a negative outside and a negative inside. Let's just go ahead and cross those out. And I'm going to plug in b and a in for my limits of integration. My answer then is going to be lambda over 4 pi epsilon naught multiplied by 1 over b minus 1 over a. Now, of course, if I don't want my lambda in the equation any longer, I can substitute for this q over the length of the bar. So that's going to be q over 4 pi epsilon naught multiplied by b minus a. And of course, we need to multiply this whole thing. Okay, and I'm running out of room a little bit. Okay, we'll try to find a place to write this. Multiply this by 1 over b. I'll sneak it in here, minus 1 over a. And we'll put that bracket around there. So this is how you find the electric field at a position located away from the bar.